Welcome back to ECE 441A, 541A. Homework number 8 hopefully will become available shortly, and I'm not sure what the deadline that will be for that. Lab number 3 is due the last day of class. Project, the first deliverable is due today, and that's really a 2-sentence or a short description with some references if you're using papers as to what you're wanting to pursue for that. And if you do not hear back from me, assume that you're okay unless you hear back from me saying otherwise. So assume that no news is good news in terms of your project. The final exam, you will want to make sure your schedule is correct because it's on a Tuesday. So if you're used to only being on campus Monday, Wednesday, Friday, you need to make sure that you're available to be here in this room at 10:30 to 12:30 on Tuesday, the 13th of December. Today, what I want to do is go over new material, and Bode plots are another way of understanding or obtaining information about system behavior, and hopefully you already are an expert with sketching Bode plots, and you should be able to do that. If I give you a piece of paper, you might be able to sketch the Bode plot. We'll talk about the characteristics of Bode plots, stability margins, and system identification. Can you really take the Bode plot and find the transfer function? So it's the inverse. So if we were doing Laplace, one direction is the Laplace, the other's the inverse Laplace. In this sense, with system identification, you're really doing the inverse Bode plot. You're extracting the transfer function from the magnitude and phase information that the Bode plot provides. Chapter 8 deals with the sketching and the analysis or the characterization of a Bode plot, and Chapter 10 gets into the appropriate design aspects that we will deal with, which are phase lag and phase lead controllers. These are the sections then that pertain to the Bode plot in the different chapters. And if you want to look at someone else's sketch or some examples, table 8, not 5, 8.2 in the new edition of the textbook has typical transfer functions, and the table that we were looking at for root loci with respect to examples, those same systems, they have Bode plot sketches for those same sketches systems in table 3 of chapter 9. I'm going to scroll through a few things and then I'll slow down in a little bit, but Bode plots give us information about the system's frequency response. We're really exciting the system at a given frequency and measuring how its magnitude and phase behave in response to that source of excitation or that frequency source. And you can think of it really as walking up the imaginary axis. If you walk up and remember the circus tent that I was talking about in 320, now if you walk up from the origin and just go up j omega, and if you stop at omega equal 0.1, and then you look around and you say, what's the magnitude of this transfer function at this point? What's the phase? And you know how to find those. You can get out your dividers and measure the lengths from the poles and the zeros and take the ratios. That's going to be your magnitude. And if you get out your protractor and measure the angles to that location, that will be your phase at that particular point. And you just keep walking. You go up to 0.2, omega equal 0.2, and you take magnitude and phase. And you're sketching that as a function of frequency. Two different curves, the magnitude curve and the frequency curve. And that tells you how your system will behave for certain sinusoids. So you go up to omega equal 1 and you shake the system at omega equal 1 radian per second. And now you compare your input frequency to the output frequency of the system. and you see maybe that the magnitude has gone down or gone up based on that frequency's response, and how much lag or advance is there between the reference input sinusoid and the output sinusoid that you're seeing. And that gives you your magnitude and phase information. And what I want to do now is see if we can sketch this for G of S. Now, if we're sketching Bode plots, it's nice to know where the poles and zeros are, and in this particular transfer function, it's written in pole zero form. The factors are factored in such a way that you can immediately see the locations of your poles. We do not have any finite zeros. But this is not the best form for sketching Bode plots. Bode plots like to have the transfer function in time constant form so that each factor, the magnitude or the impact on the magnitude of that factor has been factored out, so that when you look at that or you start examining each individual factor, the magnitude has already been accounted for in the gain constant of your system. By that I mean, if I wanted to try to translate this, this is the pole zero form. If I want it in time constant form, I'm really normalizing the constant factor or the constant term in each factor. In this case, I haven't changed the numerator yet, but if I factor out the 2 from the first term, I haven't changed anything. I can't add something other than 0 to an expression, and I can't multiply by anything other than 1. I can't modify the system when I'm trying to find how does it perform or behave. I can do the same with the second factor, and now I have it in time constant form, except typically I will consolidate all of those constants into one number. And I've selected these numbers to hopefully be clean in terms of allowing me to quickly do the math. But here I have 1,000 divided by 100, so that I now have a constant of 10, and in the denominator I have my 2 pole factors. Now I'm set to go in terms of sketching magnitude and phase. And this one's, whoa, I need to give myself some space. You're not seeing anything there. I'm just cutting my paper. And then I'll tape it back up after the fact. But now what do I have? Do I have any poles or zeros at the origin? Those are the terms that give me information at all frequencies. Do I have a pole or zero at the origin in this transfer function? No, so that makes this transfer function a little easier to sketch, maybe. If I said low frequencies, what's the magnitude of this system, or what's the DC gain of this system? Can you tell me? 10. Since I've put it in time constant form, if I put S equal to 0 or S equal j omega and say omega equals 0, the imaginary piece goes away, and in the denominator I just have a couple of 1s multiplied together, and I can actually do that multiplication, and then I simply have the 10 left over. So the DC gain is 10, and now I know that my magnitude is starting at 20 log of that number, which in this case is 10. And base 10 logarithm of 10 is 1, so now my gain at low frequencies is 20 dB. The reason we sketch the Bode plots in dB is because you can add logarithms. We have these factors that are multiplied together, but if we now take the log of this and sketch that, now we're just going to be adding those pieces together. And that allows us to easily just sort of think of each individual piece and add them together. For the magnitude on this one, if you were sketching this on the back of an envelope or on a napkin or something, you would say, oh, this is just starting flat at 20 dB. That's supposed to be a flat line. Now, I'm flat in magnitude until I reach a polar zero that changes the slope of that line, of that constant. And what's the first frequency that I reach? It's a dreary morning in Tucson. I better stop. What do we have? We have two poles, no zeros. We're only going down. Oh boy, if we're only going down, it's really going to get bad, huh? But now if we have 20 dB, we hit which pole first? The pole where? At s equal minus 2, which is a frequency of 2 radians per second. And that then, since it's a pole factor and it's in the denominator, we're going to be decreasing, or we're going to be changing our slope at 20 dB per decade. And if I wanted to, I don't know that I want to, but let me see if I can. Suppose that I say this is now 1, and this is maybe 0.1. This is 10, 100, and 1,000. And this is radians per second. Now I haven't gotten to 2 yet, and where is 2 relative to 1 and 10 on this logarithmic scale? This is actually log of omega that I'm sketching so I can get more information on a compact piece of paper. What's the log of 2? Does everybody have that memorized? 0.3. Whoa, that was quick. Maybe I need to ask the right questions. Maybe I'm not asking the right questions when I said frequency. Maybe I just need to start talking logarithms. So the log of 2, I've about forgotten what I asked, is 0.3, right? Roughly. So we're 30% of the way between 1 and 10. And so if I eyeball that, there is roughly 2. Now I would be going here, and at 2, I start to decrease at 20 dB per decade. And that means that at 20, if that's 30% of the way towards 100, now I should be at 0 dB. And if this is 0 dB, then I would be sloping like that. And I would just keep sloping until I reach the next pole. Whoops, that's supposed to be the same slope. Shouldn't have stopped. But where's 50? It's between 10 and 100. Now what's the log of 5? That one's about 0.7. So now I'm 70% of the way between 10 and 100, and that will be 50. And if I eyeball that, or if I'm 30% of the way away from, now I'm going flat until I reach that point, and at that point, at 50, I now go down even more. I change my slope again. I was decreasing at 20 dB per decade. I increase another, or I add in another slope change so that now I'm a net minus 40 dB per decade. So that if I was a little bit below 0 here, now at 500, I would be where? Let's say I was at 6 dB at 50. Where am I going to be at 500? If I was at minus 6 dB, and I'm going now at 40 dB per decade, I would be at minus 46. So I would come over here and find minus 46, wherever that is. Here's, let's say, 20, 40. Let's now say it's about here. And that's supposed to be a sharper slope. And then at that point, from there on, I don't change. This is now, because I only have the two pole factors, this is minus 20 dB per decade, and this is minus 40 dB per decade. That's the magnitude. The phase curve is a little more interesting. Why? Because how much phase can one particular pole produce? It'll give us minus 90, won't it, at the most? It's going to, before it kicks in, it's 0, and at the most it gives us minus 90 degrees. So in this case, we have to not only turn on the influence of the 0 of the phase of each factor, but also we have to kick off the slope after we get so far beyond, and we just agree that the change of that phase is spread over 2 decades, and it's centered right at the break. In this case, then, the phases are going to start a decade before 2, which is 0.2. It will go down at 45 degrees per decade, since I'm spreading that 90 degrees over 2 decades, and then it quits giving me slope a decade beyond 2 or at 20. The pole at 50 does the same, except now it starts at 5 and finishes at 500. Whoops. Can we keep track of all of that? And maybe I should try to have my scale about the same. Ugh. So here, if this is 1 and this is 2, then I'm going to say this is 0.2. And this is now 10, so this is 20. Then I change something at 5, and I go, that's supposed to be a flat curve, but 50 out to 500. And I like to actually just put all of my pieces together, and then I worry about adding them up later. For example, I would say if this is now minus 90 degrees, I have two factors that are going to eventually get me to that location. The first one is going to kick in at 0.2 and go to 20. You can do a better job of sketching than I can, especially on your piece of paper. And the next one starts at 5 and finishes at 500. And those are now my two pieces that now contribute to my phase curve. And if I now wanted to put all of those together, I would be flat. These are just straight line approximations until I go hit my first contribution, which is at 0.2, which is a decade before 2. Then at 5, which is a decade before 50, I now have both pole factors contributing phase. So at that point, I'm going down at minus 90 degrees per decade until 20, which is where my, what am I doing? Let me see if I can, does that look a little different in slope? And now what happens? Beyond 20, what happens? How many pole factors are contributing slope? Just one, and it's contributing 45, so that now, if I back this off, this should be parallel to my earlier curve that was between 5 and 500, and then beyond 500, I'm flat, and this should be now at minus 180 degrees. A straight line approximation of my phase, then, is this red curve, and my previous curve in blue was the magnitude. This is now the phase of g of j omega. And that wasn't that hard to sketch. That was probably quicker if I didn't have all this explanation than having your computer fire up and get into MATLAB. But you can quickly sketch these in MATLAB to do a check. You can just say Bode, B-O-D-E, with the system transfer function, and it will produce the Bode plot. In this particular case, this transfer function, g of j omega, that we're sketching the Bode plot for, is just this open loop block, and we want to now infer closed loop information from the transfer function behavior of g of s, where g of s could be the plant g bar combined with the controller g sub c. Eventually, we are going to be designing g sub c to give us the shape of this frequency response that we want. That's the idea. Now, what's the closed loop transfer function if our open loop transfer function we'll just call g? In this particular block diagram, what is the expression for t? This is our cheer, so we need to get up. I guess we needed some zero factors to get us up instead of just continually having pole factors that put us down. But if we had zero factors in there, the slopes would be positive or going up in the same amount, just in the opposite direction. What is T of S? I'm just going to assume that that was just blaring out and it was very dominant in terms of response. It's G over 1 plus G. That's the closed loop, and we have now the frequency response of G. We want to figure out what might happen to T, because we're really interested in the closed loop, and can we adjust G through maybe G sub C to shape it differently if we want to shape it differently. We know how to do that if we're talking about a root locus. Now we want to think about that in terms of a Bode plot or in terms of frequency response. So let's look at now the big picture insight that we can achieve from the Bode plot of G of S relative to the closed loop transfer function T of S. Or we're trying to obtain information from the Bode plot of G of S, and that can be helpful in learning about or understanding the closed loop system properties. One, let's look at, suppose that I now look at my Bode plot and I find frequencies omega where the magnitude is large. And in general, in this particular Bode plot, maybe we say 20 dB is large, but the magnitude is bigger at low frequencies than it is at small frequencies in that magnitude plot in general. Now, if it's really big at low frequencies, or if G of j omega is large at small frequencies, what can we infer about the closed loop transfer, the closed loop behavior? If G is really big in this expression, and G in this case we're just thinking about its magnitude, so now think of a big number. We have a really big number divided by 1 plus that really big number. So a really big number and 1 plus a really big number, how close are they? They're about the same, aren't they? So now we're taking the ratio of that. What's our closed loop transfer function behavior in terms of magnitude at low frequencies, maybe when our g of s is very big, when the magnitude of g of j omega? What's t? It's going to be close to 1, isn't it? And what is this closed loop transfer function? It tells us the gain that we will experience in going from the input to the output. What happens between the reference input and the output at low frequencies if we have a big magnitude for our transfer function is now the output's going to look very much like the input in terms of value because it's getting scaled by 1, g over 1 plus g. If we now have g of j omega large at small frequencies, that tells us then that the closed loop transfer function has a gain near 1 at those frequencies. And as I was trying to describe, therefore, there is a small error between the reference input and the output when we have reference input signals at those frequencies where the magnitude is big. So there's a small error between the reference input, or they look almost the same in terms of magnitude or value. This error is small between the reference input and the output for reference input signals at frequencies where g of j omega is large. What can we say about the stability, or what would we be examining in this closed loop transfer function if somebody wanted to know, is that system stable, or what's its behavior? What particular piece of this whole for t of s would you be focusing on if you're wanting to know stability? The denominator, the 1 plus g of s. So now we want to look at 1 plus g of s, and if we have g of s as a function of frequencies, 1 plus g of s isn't that much different, is it? It's not hard to sort of understand. So stability of the closed loop system is governed by the denominator, or this 1 plus g of s. And for that reason, then, if 1 plus g of j omega is close to 0, because we're looking for the values of s when that vanishes, now we want to know, are there frequencies omega where this vanishes? Then that's going to be right on this stability border. So if 1 plus g of j omega is close to 0, then we know we are near the stability boundary, or we could be near instability. Let's look now at the stability boundary. At the stability boundary, we have 1 plus g of j omega equaling 0, and now you know how we have done that for the root locus. In the root locus, we were looking at the entire S-plane. Were we not? We were looking at all values of S. Now for the frequency response, we're interested in how this system behaves to sinusoidal inputs. We're focusing on just the imaginary axis, and that's why we replace S with j omega. And we want to know, are there frequencies where this expression might be true? Or when is 1 plus g of j omega close to 0? Or another way of looking at that would be, since we have g of j omega sketched, we have its magnitude and we have its phase, now we want to look at, is it possible that those two play together in the right combination to give us a magnitude of 1 and a phase of minus 180? And if they do, then that's at the stability boundary, or that is the stability boundary. Or, when is our magnitude 1, and where is 1 on a dB plot? What's the value of 1 in gain in dB? If we took 20 log of 1, it's 0 dB. So now we're looking at values of our Bode plot that have a value of 0 dB and a phase of minus 180. And we want to know, or we are interested in, the behavior of that frequency response which we are now just calling g of j omega, near those 2 points, a magnitude of 1 and a phase of minus 180 degrees. And we're really interested in, is it possible that those are at the same 1 and minus 180 at the same frequency? And if they aren't, then we want to know, oh, if I'm at minus 180, how much magnitude change is it going to take before I get to 1? And then I would be in trouble. Or if I'm at 1, how much phase change can I tolerate before that phase gets to minus 180? I'm interested in when these two are simultaneously at 1 and minus 180. And those particular, let me say, distances are called the stability margins. For example, let's just say that I now have a magnitude plot that does this. Maybe it looks like that. And you can see where that might be a possible plant. Now let's say that our phase curve, I'm running out of paper. Now I'm going to have to collapse. But let's say that now our phase of g of j omega is something that does that. And now I need to put my lines on here that are important. Let's say that this line is now minus 180 degrees, and this line is 0 dB. And where those particular magnitude and phase points cross those magic places, one where the magnitude is 0 dB and one where the frequency or the phase is minus 180, we give those particular frequency descriptions. This is now omega sub g. This is our gain crossover. And this point is our phase crossover. So I'm going to say that omega sub g is called my gain crossover frequency, or just the gain crossover. And omega sub p is the phase crossover. And we just said that when we have this combination of phase at minus 180 and gain at 1, we have this stability issue. We're right on the stability margin. In this case, our phase is not quite at minus 180 when we have a magnitude of 1, is it? So we actually have this much margin before we go unstable. And this we call PM, or the phase margin. And the other frequency, the phase crossover frequency, provides us with information. How much can we crank up the gain before we go unstable? You now have a feel for that from the root locus. You know that if in a three-pole system, if you crank up the gain enough, you're going to cross over the imaginary axis and go into the right half plane. Well, that's the same thing here. You're just seeing it differently in terms of a frequency response. Now, how much can we increase the gain before our phase is minus 180 and our magnitude is 1? We have all of this margin, which we call GM, and that's our gain margin. If that blue curve of our magnitude was above 0 dB when the phase crossed minus 180, then we could have problems. We have no gain margin. Okay? So in this case, our gain margin is quite high, but we don't know what the axis is as far as how much it's labeled, but let's say that that's now 40 dB of gain margin. Our phase margin, maybe that's 90 degrees. But we have positive phase margin and positive gain margin in this particular sketch. What if we wanted to increase our phase margin? How could we do that? Do we have any phase margin or any phase that would allow us to have a bigger phase margin? At lower frequencies, is our phase even smaller than what it is at the gain crossover frequency? So can we make PM bigger? We could if we did what? If we made the gain curve do something like that. How can we make the gain curve do that? What happens at that kink? I didn't call it what I normally call it, a break, because I didn't want to give you that much of a hint. But that's a break frequency. So now if we introduced a pole at a lower frequency, we would start rolling off our magnitude curve sooner, which would cause our gain crossover frequency to be reduced, and then we would have a larger phase margin. Because now we would be coming down here, and we would now have that for our phase margin. Or we could introduce a controller that would manipulate the phase and bump the phase up, put a phase lead controller in to arch that phase up, and now we have a bigger phase margin that way. What we want to do now is understand how do we design controllers to adjust or compensate the phase margin and gain margin. Now we have a different way of thinking about stability and how we can adjust or enhance that behavior. For these compensators or controllers, are used to improve or adjust the nominal Bode plot of G of S to improve the gain margin and or the phase margin. And before we get, let me look at one more example, but before we get too far into that example, I want to talk about one other concept that we've been, maybe terminology we've been using, and it's maybe not as clear as what I would like for it to be. Suppose somebody gives us this system. G of S is 4 S plus 5 over S plus 0.1 S plus 20. In terms of a description that we started the class with, is this in time constant form or pole zero form? This is pole zero form. We can immediately see the poles and the zeros. So this is now pole zero form. And where are, relative to the imaginary axis, where are these poles and zeros located? Right half plane, left half plane, a mix? These are all in the left, aren't they? And so this is, you might hear somebody refer to this as a minimum phase system. And if they do, typically they're referring to whether or not you have zeros, but in fact, we want all of the poles and zeros in the left half plane before we can start talking about a minimum phase system. Where does that terminology come from? So let's just sort of do an aside to learn a little bit about minimum versus non-minimum phase systems. If I had, let's just say I'm right there for 1, 0, and the comparison 0 is right there at plus 1, just for values to think about. Here is my 0 that's in the left half plane, and this one we refer to as a minimum phase. In comparison to one that's over here, and this one we would call a non-minimum phase. And let's try to understand where that's coming from. Suppose I wanted to know, now I'm walking up the imaginary axis. That's what this is. This is now the imaginary axis in the S-plane. And this is the real line. Suppose I'm at this particular frequency that I've indicated by a red dot. What's the magnitude associated with this minimum phase 0? How do I find it? The magnitude of that factor. I simply walk over to the real line, to the imaginary axis, and then go up to omega. So now I have this Pythagorean theorem. I can now find the hypotenuse, and that's the length from this 0 at minus 1 to that red dot, to that frequency. Or I now have this particular magnitude for that frequency and due to this particular 0. What about if I had a 0 over in the right half plane and I wanted to know its length to that same frequency? Again, this, just for comparison purposes, my zeros are the same distance on the real line from the imaginary axis. Is the length any different? No. Have the same horizontal distance and the same vertical distance. That length's the same. What about this angle? The angle that I have to look from minus 1 to omega is not very much. Let's say it's 25 degrees. But what's the angle that I have to look if I have to look from plus 1 to j omega? It's now this angle. So let me call this theta sub 0 on the right, and this is now theta sub 0 on the left. Do you see that those angles are different? Which one's minimum? The one associated with the 0 on the left half plane. So if you have poles or zeros in the right half plane, those are referred to as non-minimum phase. The magnitude behavior looks exactly the same. If somebody gives you a Bode plot magnitude and they say, oh, this system is minimum phase, then you can identify that system from that information, because you know that the magnitude is produced by all poles and zeros in the left half plane. But if they don't tell you where your poles and zeros live, that magnitude doesn't really matter whether you have poles in the left or in the right or zeros in the left or right. They have the same magnitude. It's the phase that causes the difference. If we went up and looked at a different frequency up here, I think it's clear that the lengths are still the same, but the angles are quite different. And we could do that even in a table form, just to make it even more clear if it's not already. On the left, our zero factor looks like that. On the right, our zero factor looks like that. So that now our 0 is at -1, and here our 0 is at +1. But if I wanted to know what is the length of this factor, now what's the length of j omega plus 1? That's now simply the real part plus the imaginary part, or the square root of 1 squared plus omega squared. What's the length of our factor in the right half plane? That's the magnitude of j omega minus 1. Lengths are the same. But what's the phase? In this case, we have the phase of j omega plus 1, which is now the inverse tangent of omega over 1. But if we wanted to know the phase of the right half plane, 0, now we have the inverse tangent, and some calculators keep track of this. Oh, I had a -1 in the denominator. Oh, now they know that that's something bigger than 90 degrees. Some calculators will still just give you the acute angle and they'll say it's negative. So you have to be careful about what your calculator may or may not be producing. This is now the minimum phase piece or factor, and this side is the non-minimum phase. And what I want you to now do for homework on your napkin is sketch that Bode plot. What are the steps? How would you do that? First, you'd want to put it into a time constant form. Once it's in time constant form, now you have the pieces that you can work with. You can find the magnitudes individually and add those up. You can find the phases. Where's your phase going to start? At what angle? At low frequencies, what's the phase of this system? So plug in S equals 0 and you get just a positive number, don't you? So it's 0 degrees. What's your phase at large frequencies? It's associated with the pole 0 excess, is it not? You have minus 180 degrees from the poles, but you have plus 90 from the 0. So you're getting minus 90 degrees. You need to be thinking about these kinds of end pieces when you're putting these Bode plots together. and we'll pick up at that point somewhere close, maybe not so close to stability on Wednesday.